podcast is brought to you by LMU Munich.
During the lecture today. Okay, so what we were doing yesterday, the last thing we were doing was we were looking at this Recursion algebra, which came from Fourier expanding the constraint. And so, of course, similarly, everything I say for the left-moving oscillators will apply to the right-moving oscillators associated to T minus minus. And naively, we had this. But we had to normal order. But if you recall, normal ordering only affected L0. So if you like, normal ordering, you just put dots there when P is not 0. But L0, normal ordered, well, you can write it as a alpha prime over 4 P squared from the A0 squared terms, then a whole bunch of oscillators, which were A mu Q minus QQ, and just Q equals 1 to infinity. That's how we defined it. But of course, this left us with an ambiguity in the physical state conditions. Okay? So let's move these away. Then what we showed was that if I compute LM ln, ignoring the normal ordering for now, I just got m minus n lm plus n. So of course, you've probably noticed this already, but these Fourier modes are sort of additive, right? So the left-hand side has index p, and the sum of the Fourier modes here is p. So that's a simple rule to keep in your mind to check your calculations. And here again, m plus n and m plus n. And of course, this, in some sense, you knew had to appear because this is antisymmetric in m interchange n. So you have to have something here that's going to be antisymmetric in m interchange n. Okay. But that, unfortunately, for all due respect to Mr. Witt, is not particularly interesting. What is the great foundation of string theory is that we have to look at the normal ordered version of this expression, right, in the quantum theory. So this is, if you like, the classical algebra. We want to know what the quantum algebra is. So we have to worry about normal ordering. Well, the first thing you might notice is that, well, if L0 never appears, then we're done, right? Because normal ordering only affected L0. Well, that's good. So over here, you only have to worry if one of these is 0, and over here, you only have to worry if m plus n is 0. But also, the difference between L0 and its normal ordered form is just this infinite constant. And that constant will commute with everything. So it doesn't matter if L0 appears on the left, because that constant is just going to go away. All that it can never matter is if you hit L0 over here. So, in the normal ordered form, you can guess, or perhaps a better word might be deduce, that the normal ordered expression will be like this, but I might run into some problem when m plus n equals 0. So I've got the constraint that when m plus n equals 0 there, there'll be some number here, which in principle could depend on m, and it does depend on m. And also, you can figure out that this whatever appears here is going to be is just the identity, because again, it all boils down to the fact that L0 is being modified by a constant. So you have to compute this C of m. It has an obvious property that C of m is minus C of minus M, because M interchange N gives you a minus sign. Okay, so you could, of course, go through the computation with these definitions. It doesn't seem that bad, but actually it's one of the notoriously bad things to try to do. Bad meaning lengthy computation. So we don't have time to do that, and nor did, for example, Green, Schwarz, and Witten, where I'm going to steal this argument from, is you can just deduce C by some other arguments. You can compute it, but trust me, it's pretty lengthy. So the following trick I've lifted from Green, Schwarz, and Witten is, you impose the Jacobi identity on the what do you call these things? Lie brackets. Okay, so that would be the following. Oops. Is that right? MNK, MNK, MNK. Yeah. Okay. So of course that's got to be equals to 0. And the clever thing to do is to choose M and N and K such that they all sum up to 0. So choose. But that no pair sums up to 0. No pair sums up to 0, of course, means that, on the other hand, neither one of them is equal to 0. Well, what does that do for you? Of course, the fact that no pair adds up to 0 means that when I compute this first bracket, I only ever get the first term and not the the term of C, by the way, is called the central term. And C is called the central, we'll see, it's related to something called central charge. So the central term won't contribute in the first commutator because I'm choosing no pair to sum up to 0. On the other hand, it does contribute in the second one because I have chosen all 3 to sum up to 0. So when I do this, I expand and I get a whole bunch of stuff that's proportional to the first term, then a whole bunch of stuff proportional to the second term. And it's the second term that we want. And if you evaluate what you get m minus n from here times C of k. And then from there, you'd get n minus k from this commutator, and then C of m. And then from there, I get k minus m C of n equals 0. Right? So that's the coefficient of the central term in this expression. Okay, so now you just make a smart-ass choice of what to do, and that is k equals 1 and m equals minus n minus 1. Okay? So indeed, the sum of those things should be 0, but none of them is 0. Okay. Oh. Yeah.
Is there any physical reason to impose Jacobi identity here?
A physical reason?
Yes. Why would you want it to be a Lie algebra?
Well, you know it is, because it's a commutator of objects.
Jacobi identity is satisfied, then it's a Lie algebra. But it has to be satisfied.
Well, we're going into dangerous territory here, but it follows from the associativity of the of the algebra, right? And secondly, you know, I guess these are not matrices, they are infinite dimensional, but you certainly would expect from well, again, it boils down to associativity that it just has to follow, right? It's, look, I'm tricking you. I'm doing a shorthand computation to deduce this. But if I did the full computation, it would have to be true, just by definition of these operators in associativity. Right? I'm just trying to shortcut out a calculation. But if you really went and did the full hard-blown calculation from the definitions, I think you'd have to find the Jacobi identity, right? Because if you just expand out all the terms in Jacobi, they cancel, assuming associativity. So I mean, maybe, on the other hand, I don't know, maybe you could dream up something really weird where there was some non-associativity going on. But let's not go there. Okay. Right, so we substitute this in, and we're going to get basically what it's going to give us is a recursion relation for this C of n. So if you substitute it in, it's not very anything. You get 2n plus 1 from this one times C of 1. Then from here you'll get n minus 1 C of minus n minus 1. And here you get k minus n is 2 plus n, C of n. So this term you can use the fact it's antisymmetric to get you, odd function. To write it like that. So you can see you're getting a recursion relation that tells you what Cn plus 1 is as a function of Cn. And you look for it. Okay. Well, first thing, you might think this is a difference equation, not a differential equation, difference equation, which tells you step n plus 1 is a function of step n. And so if I know C of 1, I'll know C of 2, I'll know C of 3, and yada, yada, yada. But actually it breaks down at n equals 1. It doesn't tell you anything. The denominator is 0, but actually the numerator is 0 as well. So what it means is you need to input C of 1 and C of 2. And then you can crank away. And what's the solution? You can solve it. It's a particular lightning. And in fact, the solution is that C of n is just any constant times n cubed plus another constant times n. So if you want, I do it in the notes actually, you can substitute this in here and it just cancels. So, okay, it's cubic. And remember, we inputted that it was odd. So we now got two constants, C1 and C2. Well, 2 is always much worse than 1. So what do you want to do about C2? Well, you can get rid of C2 by simply arguing that by shifting L0 by a constant, which is what we're all after about, this constant A, you can change the value of C2. So is that up? Can you read the top board? Yeah.
Why do you consider such m and k that the sum is equal to 0?
It's just a nice trick.
It's just of n equal to 4c.
Yeah, all we're after is computing C the quickest way I know how, with the least pain. Yeah. What I can recommend you can do, if you like, is just don't do that. It's more helpful when you know the answer. Take the answer and compute this the top line, and without assuming this, and you'll see it vanishes. But I'm just doing it as a trick to get to here. And my next trick is to say, well, listen, since L0 for all intents and purposes is only defined up to a shift by a constant, I can shift it by a constant, and then that shifts the linear term in this function C of m. right? Because when I have m equals n, I get a 2m factor times L0, and if I shift L0 by a constant, I can shift the linear term here. So actually, without loss of generality, we can fix. The usual one is C2 equals minus C1, which is the traditional choice. So that's from redefining minus constant. And since that constant was arbitrary and ambiguous, we're free to do this. Okay. Yeah. Sorry, k equals 1. Well, remember, this is just a trick to get this. Well, so remember, this is all a shortcut for an honest calculation. If you do the honest calculation, you will compute C. And so C exists, and the answer is of this type. So if you actually know the answers of this type, you're just choosing the fastest route to find C. And I found it like this. If you want, you can now go back and put this into that expression, and don't assume anything about n, m, and k, and you'll see it works. SO2?
No, if you put C2 equals minus C1, that means that there is the SO2 subalgebra.
Oh, the SL2 subalgebra, yes, sorry, SL2, yeah.
So in principle, there may be so that it isn't there. Well, yes, if you don't involve this
The oddness? But okay, but then there would be an algebra that simply shifts by moving one of the generators by a constant that would give you the SL2. So it's like I say, it's a shortcut for a long calculation that gives you this answer. So there is an honest calculation. But actually, I think when I had my course in string theory, when I was a master's student, I think we did do all this. And I think in a course of 12 lectures, we got about as far as we got today in these lectures because of doing all these details. And my God, was it boring. And it was on a Saturday morning at 9 a.m. Anyway. So we now have got as far as suggesting that, well, not suggesting, hopefully convincing you, but I can see the skeptics. Some constant, C1 I guess we're calling it, m cubed minus m. So this isn't a function anymore, this is just a constant. So let me write it this way. M squared minus 1. Okay, so now we're down to computing this one other constant, C1. And again, we're going to do a trick. Yeah? So the trick is just to evaluate it on a particular state. And the state is L minus 2 acting on the vacuum, and the vacuum with 0 momentum. Okay? Because if I do that, I can sandwich in here L2 L minus 2, yeah, commutator. Okay. Well, this is just equal to this. Well, no, not quite, actually. This is just equal to L2 Oh, wait, actually, let me jump the gun. Let me jump a step. Let's just evaluate the expectation value of this. So the point is, on the one hand, this it's the commutator, but actually only the first term contributes, because the second term, where there's L minus 2 and L2 here, annihilates this vacuum state. So it is just this. So if you think of this as being some state chi, then this is this is just the length of chi. On the other hand, you can use this algebra to evaluate it. What do you get? Well, of course, from here. So this, on the other hand, is equal to 4 L naught plus C1, and then m equals 2. So this is 2 into 3, 6, right? So 6. Okay? Now, L naught acting on this is 0. Why? Well, because the momentum is 0. So remember, this is alpha prime p squared over 4 plus the normal ordered this expression with positive moded oscillators. So these kill the vacuum because it's normal ordered, and this kills the vacuum because I'm just taking the vacuum at 0 momentum. I could have taken a vacuum with p squared equals 0 too. So this expression here is just 6C1, and I'm going to assume the vacuum state is normalized to unit norm. Okay, so this is just 6C. All right, so roundabout way we've got to that equation. So I leave it to a problem for you to compute the norm of chi the hard way.
Do you understand correctly that in order to calculate C1, we should use the definition of A2, and then it's possible to calculate C1? Or it's
Yes.
another trick?
No, it's no trick. So the problem is, given the definition of L minus 2, acting on the vacuum, compute its norm of the state chi. Ooh, a bit enthusiastic there. There are no tricks in the problem sense. Well, yeah, so the problem is from definition compute chi and show what do you get? D over 2. That's, of course, assuming the vacuum is normalized to 1. So the bottom line is that you get that C1 is D over 12. Okay? And this number, in general, C1, well, actually, it's normalized differently. In general, this number D is called the central charge. And here we're seeing the central charge is the number of fields X. But if you do conformal field theory, people talk about central charge every 5 minutes, and in principle it can be something quite different. But for free fields, it's normalized such that you get 1 for every free boson. Okay. I got another problem for you. Actually, I got enough from here. So now we can construct all sorts of states in our theory, but there are some oddities. So we construct, if you do this problem, that's fine. But there are states with negative norm, right? So, actually, let me change the one. So we've got this Fock space, and then we impose the constraints on this Fock space to get the physical space. But it's a little sick. A little or a lot, depending on your perspective. But it's not really sick. It's indicative of something called gauge symmetry. So for example, I might construct this state, A minus 1 on the vacuum, with some momentum, with some index here. What's its norm? Well, this is called the state, well, for lack of a better word, A mu. So I'm not summing over any mu index. So take its expectation value, just bracket notation. There's a dagger here, so that converts that to +1. And then A minus 1. So there's no sum on mu. But I can replace this by the commutator, because this would annihilate that. But I know what this is. This is eta mu mu times 0p. Well, the problem is that eta mu mu is not always positive, right? It's got a minus sign for time and plus for space. So there are negative norm states. So A0 minus 1 has negative norm. And here's a simple problem. Show that A0 minus 1 plus A1 minus 1 on the vacuum has 0 norm. So basically, the metric on the space of space is being inherited from the metric in space-time, and just like you've got space like time like a null, in space-time you have space like time like a null in the Fock space. Well, it gets even weirder than that, actually. I'll give you a definition. It has a state which is called a null state, which is a special case of the states that have 0 norm. This is old language. So, definition. A state is null if and only if, well, 2 conditions. It is a physical state, and 2, it's orthogonal to all physical states. So not only is it orthogonal to itself and hence has zero norm, it's orthogonal to every other physical state. So this Fock space is huge with lots of sort of disconnected pieces, if you like, or orthogonal complements. Now, okay, I better give you an example of one of these, because perhaps you don't believe me. And actually, a useful example is the following. All right, let's look at a state called chi, which is L minus 1 acting on the vacuum with momentum p. Because it's L minus 1 times something, it's clear that it's going to be orthogonal to every physical state, because chi physical state is the vacuum p onto L plus 1 physical state. And that's going to be 0 because L plus 1 will annihilate a physical state. These states are sometimes these are called Virasoro descendant states. Anyway, okay, so indeed it's orthogonal to every physical state, but I have to check that it is itself physical. Right, that's not too difficult. I could give a whole other lecture during the time it takes. Okay. So now I have to convince you that this chi is physical itself. So what do I have to do? I have to look at L on these various states. So let me first do L naught on chi. Oh, by the way, I'm going to stop writing normal orderings now. Everything's normal ordered. The L's are L normal ordered. You can, right, just save the handwriting. Okay. So this, of course, is L naught, L minus 1 on 0p. Now, L0 on 0p is 0 if p squared is 0. We saw that earlier because it's p squared plus positive oscillators. So it's going to be 0 if p squared is 0. So if this is a massless state. Okay, so let's take p squared to be 0. Well, in particular, then I can use the algebra again. Right, because when L0 hits the ground state, it gives 0. And now I can use our algebra. That gives me L1 from the first term, and that's it. Right, the central charge term won't be there because 0 is not equal to 1. Well, that's what we want in some sense because it tells us that L0 minus 1 onto L1 0p, which is L0 minus 1 on this chi, is 0. So this is a null state for the magic value of A, which is A equals 1. So here you start to see something special happens when A equals 1. What happens is you get a lot more null states than generic values of A. All right, I'm not done yet though. I have to evaluate the higher L's. LP on L naught 0 chi. Well, that's slightly easier because, of course, it's obvious that I can replace this by the commutator. Because I'm only interested in p greater than or equal to 1. So that automatically annihilates, minus 1 on the vacuum. Okay, so this is what? P plus 1 becomes LP minus 1. And then there is a potential term from the central charge when P equals 1. But that term always goes away. The central charge, have I written it anywhere? Oh, it's gone. Remember, it was m cubed minus m. So if m equals 0, 1, or minus 1, the central charge term is gone. So this term is actually not there because it's 1 into 1 squared minus 1. So that's not there. And this shouldn't be chi, this should be 0. P, excuse me. Okay, well, so for p greater than 1, this clearly annihilates that and we're done. You just have to check p equals 1. But at p equals 1, this is L0 acting on the state. And again, I've chosen p squared to be 0, so that's 0. So this is always 0. Okay, so there you go. That's a null state. And there are plenty of null states in the theory. So what do you do about it? Well, this isn't the first time that you run into such null states in canonical quantization. You see it in this Gupta-Bleuler formulation of quantum electrodynamics. And it arises because there's a gauge symmetry. And at this level, the gauge symmetry is defined as the following, is we want to get rid of all these null states, at least from the physical spectrum. So we make an identification. We're going to quotient out the Fock space. So, two states, two physical states. Are equivalent if and only if they differ by a null state. So one physical state is equivalent to another physical state plus any null state. So this defines an equivalence relation, and you can mod out. Why is this thing? I guess if I do it this way, I don't identify. The reason why you can do this is because this will never change expectation values, because if I do take some other physical state and I take its inner product with this physical state and I do this shift, well, that's but this is 0, so it doesn't change any expectation values. So it's an okay thing to do. And it is just an analog of gauge theory. You can think of this as the vector potential plus a gauge transformation d mu lambda. If I compute anything in the theory, it doesn't depend on this lambda. And indeed, that's what it does for us. So we'll do some explicit examples now. We'll move on to see exactly what's going on.
But if you insert an operator between the states, the expectation value of operator can be changed if you add null state.
Well, then okay, but that operator, when you act on it, won't be a physical state. So, right? So you're not particularly interested in that expectation. Okay. Right. So let's go to some examples. I mean, let's do this, go back to our strings. It's been some time since we've really looked at them. Okay, so at this point, I've been more or less describing open and closed strings using the same language. I've only been writing down the left-moving oscillator, yeah?
So I don't understand what's going on with the negative norm states.
Ah, sorry, I should have said this, yeah. So yeah, indeed there are negative norm states, but I'm sorry, this is a very important statement. So there's this thing called the no-ghost theorem, it was proven back in the early 70s, early days of string theory. It says that if you consider the quotient space, then there are no negative norm states in that. Take the physical space and quotient out by that relation. Sorry, this is a very important point. Yeah, well, yeah, so that's called the no-ghost theorem. Yeah. Well, of course, that actually, yeah, well, I don't know if, I can't remember, it definitely works for a equals 1 and d equals 26. It might work for some other values as well. But yeah, this is a famous theorem back in the early 70s. So that everything's okay now. Yeah. Thank you, that's an important point. Okay. So everything I've been doing, I've been, of course, just talking about the left movers, but there's the right movers, and the right movers do the same as the left movers. But now, let's really look at some strings. I'll do open and closed. Most of this course, I really want to talk about closed strings because these days, open strings are synonymous with D-branes. And Ralph Blumenhagen is going to tell you about D-branes. Okay, so we'll start with open strings. So, of course, the string has an endpoint, and the typical region is sigma equals 0 to sigma equals pi when we do our Fourier expansion. Now, because the string world sheet has boundaries, you have to check that you have to impose boundary conditions that make the variational problem well defined. And actually, so it's a problem. Show that suitable boundary conditions at sigma equals 0 and sigma equals pi, and you treat the boundaries separately.
I've always wondered why are we doing this string length to be sigma and not pi and not 2 pi?
Why not 2 pi? So it's all convention, and it all dates back to what these pioneers were doing in the 60s and 70s. And I think the answer to that is it's quite obvious why a closed string has 2 pi. Presumably that's natural. Why has this got pi? It's not a closed string, but you can make a closed string out of it by joining 2 together. And then, right, by just declaring this point, you know, how does it work? You take this guy and you take another an inverse copy of him, and you match them there. And this would now give you a closed string of length 2 pi. And it's called the doubling trick, and it's used all the time in the old literature. But it's just a convention. In fact, it's a rather irritating convention because, well, I'll tell you in a second, but it's what everybody does. So these are the boundary conditions you want to show are that eta mu nu dx mu x prime nu must equal 0. So this famously gives rise to two types of boundary conditions. Either you set this to 0 or you set that to 0. Setting this to 0 is called Dirichlet. Setting that to 0 is called Neumann. So for many years, people refused to set Dirichlet boundary conditions because that meant that the string endpoint didn't move, right? And then it had to be attached to something, and that was clearly a ridiculous idea. Some people were literally laughed at conferences for suggesting similar things. But then Polchinski came around and told us that absolutely you must consider D-branes, and you must consider that. So that's to be done in the D-brane course, so I'm not going to touch that. I'm just going to do good old-fashioned Neumann boundary conditions. So we will take so intuitively, by the way, what's the difference in the boundary conditions? So the Dirichlet boundary conditions tells you that the string is attached to something. It's stuck. So it's like a flag ending on a flagpole. And the Neumann boundary condition tells you that it's not attached to anything. It's free to flutter in the breeze. It's like the other end of the flag. It's not attached to the flagpole. And if you look carefully at flags in an ideal situation, you will notice that, okay, one end is stuck, and the other end, it doesn't, its derivative is constant. That's the statement here, 0. And this is because it's not allowed to leak momentum off into the air. So actually, I guess you should probably look at the flag on the moon. It would be a better example, where there's less air. So if in a vacuum, a flag would not move its derivative like that, because it's not allowed to exchange momentum into nothingness. On the other hand, the Dirichlet boundary condition does exchange momentum, because if you hold a flag in a flagpole and you hold it in a strong wind, you can feel the wind, and that's because the flag is imparting momentum down the flag and onto the flagpole.
Do I understand correctly that this condition becomes from the boundary part, but what shall we do with integral of tau?
So the boundary.
The boundary is with respect to sigma.
Yeah.
But as far as I remember, there is also integral
Yeah.
with respect to tau.
So I guess you would want me to write that.
And why usually this integral is repeated?
Well, one only usually likes to consider what's called local boundary conditions. So you specified at a point. So you wouldn't want to have the boundary condition at time t, depending on the boundary condition at time in the future. So you want a local boundary condition. Yeah.
How can I bend or accelerate the D-brane?
Well,
If this is delta x 0, then it can't bend.
well, this describes a static D-brane. So then you quantize the D-brane, and then you find it has motion. And then, yeah. The other thing to note, well, another simple answer is this is, of course, Lorentz invariant, so I could boost it, at least have it moving. But anyway, ask Ralph these questions, okay? All right. So we're going to take this old classical fashion Neumann condition, and, well, to cut a long story short, when we expand out our x's, this reflects the left and right movers into each other, so we no longer have separate left and right movers. And I'm not going to trouble you with the details, but if you expand it out, you simply get a constant x mu. Now, one of the irritating things about this choice that everybody does, sigma pi, is actually I want to redefine what I mean by momentum here. I used to call it alpha prime p mu, and now I'm going to call it 2 alpha prime p mu. Okay? And that's because of the stupid factor of 2 that's missing, so that when I compute the space-time conserved charge, I want it to be associated translations, I want it to be this p. And hence I have to put a factor of 2 in to compensate for that. It's just it's a minor irritating point of strings. Well, if you expand it out now, you get the left and right movers become identified. It's an easy exercise to show that. And we've got Neumann boundary conditions here. So, okay, there's an oscillation in time, e to the minus I n tau, and you want something whose derivative vanishes. It's cos, right, whose derivative vanishes at the endpoints. So you expand it as cos. So what's happened if you go back to where it was before, you simply have that a n mu is identified with a tilde n mu because of the boundary conditions. Okay. So let me let n as an operator be defined as a mu minus n a n nu, eta mu nu. So you should recognize n as the analog of the number operator in the harmonic oscillator. And it's not hard to show. So n commuting with a mu minus k, say, is k times n, right? Is that? No, it's k times a. So what this means by classic arguments is that acting with a minus k on a state raises its n eigenvalue by k units. Yeah, this is classic harmonic oscillator stuff. So if I have a state n, which is an eigenvalue of n, yeah, so it's easy to see that n is Hermitian because it's of the form a dagger a. So we diagonalize it, eigenstates n. Then it's not hard to see that n acting on a mu minus k n will be n plus k on a minus k mu n. So acting with the creation operators raises your n eigenvalue by k units. Well, what's L0? Normal ordered, of course. It's alpha prime p squared. There's no factor of a quarter here because of that redefinition I told you about. But let's, in the exam that's at the end of this course, you won't be asked about these details. Okay. And you add n, and then the physical state condition is L naught minus a on a physical state vanishes. Of course, there are other physical states, other conditions, where the positive moded oscillators annihilate. But this is the most interesting one because you see it translates into a space-time equation, which is p squared plus the n eigenvalue, let's just call it n, minus a over alpha prime equals 0. And this gives you a mass squared. So now you see that these higher oscillating modes of these open strings correspond to more and more massive states in space-time. And there's an infinite tower of them, right? You could just go on and on and on and on and on, adding on these oscillators. Now you have to check the physical state conditions, Lp, for p greater than 1 or equal to 1, but nevertheless, you still get an infinite tower. The great bummer, if you like, of the bosonic string theory is that the ground state is tachyonic, right? Because A, it's going to be equal to 1. It's positive anyway, but we're going to see it's going to be equal to 1. Certainly lots of magic happens at n equals 1, but A equals 1, sorry. But you see that n equals 0 is a tachyon. So 0p, the ground state, is a tachyon, space-time tachyon. because p squared is minus a over alpha prime, which is minus 1 over alpha prime for us. So this is one of the problems of the bosonic string, which we're going to ignore because it goes away in the superstring. Actually, the open string tachyon is actually understood by the work of Sen primarily, and it's related to the instability of d-branes. So you can have unstable d-branes, and the tachyon in the open string spectrum associated to unstable d-branes is just mediating the decay of d-branes. But we're going to see that there's a tachyon in the closed string spectrum, and nobody has a clue about that, unless one of you does. So as far as we know, the bosonic string will be is unstable. So of course, a tachyon is not the end of the world, right? The standard model has a tachyon, right? If you expand the Higgs field around the symmetric vacuum, it's got a negative mass squared. So somebody got a Nobel Prize for tachyons. It's not that bad. But of course, the point is, in the standard model, you know what the potential. You know you're expanding around the maxima, and you know that you would fall into the unsymmetric phase, and everything's okay. The problem with bosonic strings is you know you've got a tachyon, you know it's downhill from here, but nobody's ever been able to show that it ever stabilizes. Okay. So the vacuum is a tachyon, and of course LP on the vacuum state is 0 by construction. Fine. The next thing you might want to consider is A minus 1 mu on the vacuum. This guy. Well, what's this? First of all, when is it physical? Well, it raises the n eigenvalue by 1. So, sorry, it's 1 minus A. So here, again, you see that when A is 1, the next excited mode is massless. Now that's good, because we generally expect that alpha prime is a huge number, or actually a tiny number, because it's a length. This length is the size of these strings, and they're meant to be roughly Planck scale. So if you get anything on the top that's not 0, it's going to be very massive, way up at the Planck scale, and we don't care about it. So A equals 1 is magic because you get massless modes, and hence you might explain some of the physics we see. So A equals 1 gives us this massless mode. All right, well, we have to check that it really is a physical state. So this is the L0 condition. Just tells us that it's massless. So again, I'll call it A mu. So we have that p squared on A mu is 0. Now, I have to check the other physical state conditions. So ln on this guy is what? Well, 1/2 sum on my p's of L, not L, sorry, A nu A lambda, eta nu lambda, and then I have n minus p, p, and then I put it, that's just the definition of ln, and then I put in my A minus 1 mu. P. Okay. Well, it's not hard to see that the only thing that can contribute here is p equals 1. Because if p is bigger than 1, this goes through and annihilates. Now you might worry, what if p is less than 1? Well, then this guy will come through and annihilate. So I won't do it now because I always get confused. So what you're just left with is, well, there's p equals 1, and then there's n minus p equals 1. So at the end of the day, you get just A lambda 1, A mu minus 1, 0 p, and A1 minus A0, actually. P equals 1, oh, P equals 1, n minus 1, nu, e to nu lambda. Okay, this you can replace by the commutator, right, because this one would annihilate that. So the factor of 2 goes because there's two possibilities. This one equals 1 or that one equals 1. So you replace this by e to nu lambda, a nu n minus 1. And then this is the commutator, a1 lambda, a minus 1 mu. You know what the commutator is. That just gives you eta lambda mu. So you have a mu, a mu n minus 1 on 0 p. Okay. So that's going to be 0 except for n equals 1. Right? For n equals 1, I'm going to get that p mu on this state is 0. Now you might say, oh, so I have to set p equals 0, but that's not quite right, because I can smear these things. This isn't a particularly interesting state. What's more interesting would be no, give me a second. Because, all right, so this guy is not so good, but I could consider instead, if you like, wave packets. So, because I can sum over states. So I can integrate over P in some crazy notation, some smearing function A mu of P, and then this state A minus 1 mu on 0 P. I shouldn't have perhaps called that one A mu. Now I can consider this one. It's just a sum, right? I've just summed over a whole bunch of physical states. They're physical when? Well, P squared on AP has to be 0, and P mu A mu has to be 0. If I just substitute this, right, it's just a linear superposition. So if I put those conditions onto this state, I get these conditions on the skate in this field. Now, in space-time, this condition is more accurately the Laplacian when you Fourier transform it, and this, of course, is the famous Lorentz gauge. Right? So that's a more interesting state, some superposition of all those little states. And it's physical if this is true. So I convert to momentum position space, and I get this. And you recognize that as a gauge-fixed form of Maxwell's equation, right? Because it is by default, if you put these two together, it is d lambda. So I think it's astoundingly beautiful that one starts with a string and quantizes it, and in an open string out pops Maxwell's field. It's very nice. We didn't put it in, right? At no point did we say, I want to get Maxwell's equations out. You just get them. Okay, in a gauge-fixed form, but still. Okay. And in fact, Do you want to go through it? Maybe it's worth going through it. The other thing is you can convince yourself that this state I could modify by addition of a null state, right? And the null state I might want to consider is ddp 2 pi d. Some function lambda of p, and then that null state we had before. The null state we had before was just L minus 1 acting on 0 p. This state will be null if, well, what was the condition? It was simply that p squared was 0. So you have that condition. If you work out what this is, maybe we can just do that briefly. So this is null, right? What is L minus 1 on 0p? Well, it's 1/2 sum on p, a mu, e to mu nu, minus 1 minus p, p. Right, what contributes here? Well, obviously if p is positive, you're done, and if p is negative, but negative bigger than minus 1, this one will go through and kill you. So you've only got p equals 0 and p equals minus 1 contributing. They both contribute the same because you get the same combinations here. So the only thing that contributes is p equals 0 and p equals minus 1. They both give you the same thing, which is a minus 1 mu a0 nu e to mu nu on 0p. Let's do the all right. Okay, so we've got the top board looking at the last line. A0 is just P0 up to some factor. So L minus 1 on 0P is P mu A minus, well, P mu downstairs, A minus 1 is 0P. So this state lambda is just some smeared function . So you see, when I add it to this big state that I was working with, which is the very top line on the top board, I simply get A mu is equivalent to A mu plus P mu lambda. Or in space-time, coordinate space, A mu is equivalent to A mu plus D mu lambda. I've dropped some factors of alpha prime and things in here, but you see the point, right? So these null states are generating for you a gauge symmetry. And of course, the fact that lambda is at zero momentum, at p squared equals 0, it preserves the Lorentz gauge. So there's one other thing I'll mention here, but it's really much better associated with D-branes, which I don't have time to discuss. Is, okay, Maxwell theory, that's quite nice, but you want more than Maxwell theory, you want Yang-Mills. How do you get Yang-Mills? And it was two guys, Chan and Patton, who figured out that, well, you know what you can do is you have this open string. And unlike the closed string, the open string has two preferred points, the two ends. So I can hang extra labels there, and they're called Chan-Patton indices. I can just put, if you like, a finite quantum number there, which just ranges between 1 and whatever I want, 1 and n. And then the ground states of this string are labeled by ground state, momentum, and then AB. So they pick up a matrix-like structure of index AB. And when you compute string theory with this extra bells and whistle on the sides, it looks very innocent. Everything's promoted to matrices. You get a gauge symmetry. It's all consistent, so there's only one thing it's going to be at lowest order in derivatives, and that is Yang-Mills. So this does give you Yang-Mills theory. A mu will get promoted to A mu AB, and that's viewed as a matrix, and indeed you find Yang-Mills gauge theory coming out from open strings. Okay. But that's the old way of thinking about it. The new way of thinking about it is, oh, you've got open strings. When you ever have an open string, it's ending on something, and that something's called a D-brane, and this is A and B are just labeling which D-brane it's ending on, because maybe there's more than one lying there. And that's what gives rise to these indices. Okay. But there's much more about all that in Ralph Blumhagen's lectures. Okay, are there any questions on this? Sorry? Well, I don't know, you have to compute it, but... not necessarily. It would depend on A now. So what was a negative norm state was this one, A naught minus 1, A1 minus 1. And actually on the vacuum, well, yeah, that state has got negative, that's got 0 norm. No, it depends on the value of mu, because it's the value of mu that fixes the... So only for A0, A minus 1, 0 is a negative norm state, but A minus 1, 1 is not. Actually, it's instructive. Go compute something that looks like it's negative norm here, and you'll see it's pure gauge.
I'm wondering about these massive string states.
Yeah.
So with alpha prime at Planck scale or something, they should have masses of around 10 to the 10 GeV?
Right. So it's a little complicated story. So, of course, so there is this infinite tower. I've given you the vacuum state, which is a tachyon that's unstable. And it's unstable at Planck scale instability, except by alpha prime. Then there's this lovely massless modes that we're all happy with. And then there's this infinite tower, and the infinite tower starts off at the scale alpha prime. So what is alpha prime? It's called the string scale. What is the string scale? It's actually technically different from the Planck scale. I can get into this a little later, but the Planck scale, the string scale is just the scale set by the strings, okay? So like the size of the strings. And this is actually free strings theory, so nothing's happening. What would set the Planck scale is the interactions between strings that include gravity. So the Planck scale winds up being, now I'm going to get this the wrong way around. So there has to be 1 over square root alpha prime on dimensional grounds, and yeah, it turns out to be 1 over the string coupling constant. So the Planck mass at perturbative string theory is actually slightly above the string scale. And this is important, actually, because you wouldn't want to discuss massive string modes if they were black hole, if they were highly gravitating objects above the Planck scale. But in perturbative string theory, when G is arbitrarily small, the Planck scale sits above the string scale by some separation that you can tune by G. So it makes sense to talk about maybe the first excited mode without having to worry about it being a black hole. Now, of course, you could go to strong string coupling, and then the opposite happens. Well, you do what you can do when you can do it. But in principle, there's a window where it makes sense to talk about a massive string states without worrying about quantum gravity. Oh, I just combined those two equations. I took the first one and subtracted off the second one.
Yes, but how do you got the quantum physical
That's the physical state condition. That's L0 acting on the state equals -1.
And with these string quantum indices, how can you get a nonlinear equation instead of maximum equation?
Very good. Excellent question. So you can't get it at this level because we're doing free string theory. You have to do string scattering, and then you see it. And it's related to the fact that in Yang-Mills theory, in the appropriate normalization, the coupling constant sits in the commutator. Yeah? So you can rewrite Yang-Mills theory with the commutator is always associated with the coupling constant. And we're taking the coupling constant goes to zero limit. Okay. Yeah.
I have been confused with the last string on the last line on the second board.
The middle board.
Zero p is eigenstate of momenta
Yes.
with eigenvalue p.
Yes.
And why p acting on this state is equal to 0?
Okay. I must admit, perhaps this board wasn't as transparent as it could have been. I should really have put this A mu field in front of everything. It would have been much more clear had I'd followed my notes directly and stuck here, imagine this state. Okay? And then I would get this state. And then I would get all the way down here, A mu. And then I would get here. So it's this combination A mu, P mu. Okay. Okay. I guess it's probably time to start. You wanted to make some announcements. It's a little early, but... Well, the problem is we're done with the open strings. So it's a good place to stop, unless there are any more questions.
So can we find the effective action for this mu?
Yes, you can find the effective action for A mu, and it's Dirac-Born-Infeld. Or Born-Infeld.
Like the point particle case you found between Born and
Yeah. So here things are complicated because as someone very astutely pointed out, in the point particle case, the effective action is the entire dynamics solved. Klein-Gordon equation in space-time is the quantum states of the free particle. In string theory, that's not the case because I've got an infinite number of particles with infinite number of towers, and I don't want to have to worry about the infinite tower. It's not. I just want to worry about the massless modes, so I get rid of the infinite tower. So now I really do talk about it in effective action, because I'm just talking about the physics of the massless modes without worrying about the infinite tower. So the space-time effective action now includes all sorts of effects from these infinite tower of states, and so now it really is just an effective action. It's not capturing the whole dynamics. And as a result, it gets lots of nonlinear terms from integrating out the massive modes. Yeah. Sorry, why? Oh, it's not necessarily, no. That was this point. But, well, we can discuss this, but if I want to consider a physical scattering process of strings or something, I'm only interested in the expectation value of physical states that go in. Okay, shall I hand the mic over?